In this presentation, we're going to look at some of the fundamental areas of security. This includes a basic introduction to outline some of the main terms that it will use and some of the main issues, the ISO 27702, risk analysis, and then on to security policies, a basic outline of some of the threats involved, some key principles, and then some overall conclusions. At the present time, we're moving from what's called an industrial age into an information age, where things and methods of doing things are changing. For example, our postal system is being largely replaced by an email system, paper voting by e-voting, a telephone system is now being replaced by a voice over IP system, and physical shopping by e-shopping. For us to be able to move correctly from an industrial age into an information age, there are three basic fundamentals that we need. And these three fundamentals are confidentiality, authentication, and assurance. With authentication, we aim to properly authenticate users, devices, and servers, and also even network connections. With confidentiality, we typically want data that's either stored or transmitted to be kept confidential, and this typically involves encryption. And then we want to make sure that the data, when it's stored or transmitted, has some assurance so that we know that it has not been changed. The major problem that we have is that we typically look at systems in a layered approach. So in this case, we might have our network infrastructure as a foundation. We need some application communication protocol to be able to communicate between applications and services, and then we have the applications and services themselves. And then at the end of the line, we also have the user. So the user may use an application and then use an application protocol to communicate. Then they use the network infrastructure to send the data, and then it goes back to the user on the other end. The major problem that we typically have is that each of these elements, such as the network infrastructure, can be made fairly secure. But the problem tends to be at the interfaces between these levels. So the interface between the network infrastructure and the application communication protocol and the applications themselves into the protocol can be left insecure. So the key in security is to make sure that all the elements, including the user, are kept integrated so that we have an integrated security policy. So some of the key principles for this are CIA, confidentiality, integrity and insurance, and we also get AAA, which is authentication, authorization and accounting. So the main issue that we have is typically how to keep these interfaces secure and make sure that the overall system is kept secure and integrated. A focus on one area may leave some weakness in another area. So what is it we're trying to protect against? Well, the lowest level is typically the home user. The home user is typically an individual on their own, and they tend to have a fairly limited budget, possibly of only £1,000 or so. They will typically have a PC and some basic scripting tools. This level is fairly easy to protect against. As the level goes up, then there is possibly more money involved in an intrusion. So a professional data miner might have a larger budget, and they might have some money to be able to invest in intrusion methods. As we go up, we have industrial espionage, where the budget can increase because it might involve some important design of a system. And then we have government activities, which might have budgets of hundreds of millions of pounds. And then at the top level, homeland or large-scale military activities could have budgets of billions. As we go up the various levels, it becomes more difficult to defend against. So what we typically do is that we have a perimeter for our organisation, and then we have our firewall. And it's the objective of the firewall to keep out the intrusions. So we might have data stealing, external hacks, denial of service, personal abuse, worms and viruses, fraud, and terrorism. And what we're trying to protect are our systems, our assets, our data, and obviously our users. And we want these entities to have access to email, web, and so on. The biggest problem, though, is that it's been shown that many of the breaches actually come from inside the corporate network. So the gateway firewall can only solve some of the problems, in that our problems could actually be on our own site. So this is our perimeter here. So we have a policy, some security policy or audit policy, which is applied onto the network infrastructure and then onto our servers and our hosts. We might have some event detection, which will detect certain events such as an intrusion on the network, and some network sensors which might be used to gather some information about the operation of the overall system. So we might also have server logs, event logs, host logs, and so on, and they can be used at some later time in face of an intrusion, so that the overall system can learn. Okay, so let's look at one of the most important standards related to security, which is ISO 27702. Basically, it came from, started life as the Information Security Code of Practice from the DTI in the UK, and it was published as long ago as 1990. And it's recently been standardised as ISO 27702. And basically it lists 11 main clauses which should be seen as good practice within an organisation. One of the clauses is business continuity planning, and for this it is important for the organisation to define the critical business processes, and then to have some methodology to ensure that these business processes can still work through interruptions. We also have access control, and for this we control the access to information and also limit unauthorized access to it. It also includes remote and teleworking work, which is becoming a key issue in security. Another clause relates to system acquisition, development and maintenance, and this tries to ensure that the systems are built on a secure infrastructure. It also tries to ensure that they prevents loss, modification or misuse of user data, to protect the confidentiality, authenticity and integrity of information, ensures that IT projects are run in a secure manner, and it maintains the security of application software and data. Clause 4 here is physical and environmental security, and that tries to stop unauthorized physical access to systems and data. Clause 5 here is compliance, and that's to make sure that the organisation complies with any criminal or civil law and any of its statutory or contractual obligations. It also ensures that systems abide with policies and standards. 6 relates to human resource security, and that focuses on the reduction of risks of human error, theft and fraud. It ensures that people are aware of security inside the organisational context, and it also tries to minimise the damage from security incidents and obviously learn from an incident that happens. This is actually one of the most difficult areas in all the clauses. There is organisational security, and that's to make sure that there is some management of the overall system, that they maintain control of the security of their assets and also by third parties, and also for outsourcing to other organisations. There is computer and network security, and that's to make sure that the network equipment is kept secure, especially in protecting against damage and loss of data. Asset Clause 9 relates to asset classification and control, to make sure that all the assets are tagged in some way and have an appropriate level of protection. 10 relates to the security policy for the organisation. 11 is some definition of the security incident management, and that's how to anticipate for future breaches and how they are responded to. And then 12 relates to risk analysis. Risk analysis is one of the most important areas of security, and it's the focus on trying to identify the risk to the organisation, defining the costs associated with that risk, and then defining whether it's worth mitigating it or not. A key focus in security is to make sure your key assets are kept secure. So for every risk, there is a likelihood of that risk happening. So it can be highly likely, such as that the sun will set every day, or it could have a low likelihood, such as a lightning strike. And then there is a cost associated with each risk. Might have low cost or high cost. So if something is highly likely to happen and it has a high cost associated with it, then it's probably not worth mitigating against. It's possible to get insurance that covers the costs of this event, but as it has a low likelihood, the organisation may decide that it isn't worth the investment in mitigating against it. Also, if something is highly likely and it has low cost, then it's probably worth mitigating against this risk. The most difficult areas are where it's highly likely, where there's a low likelihood and there is also a low cost, or where there is a high likelihood with a high cost. It is in these regions that it takes expert knowledge to be able to decide whether to mitigate against a risk or not. So there are many different types of risks, and for their probability of happening. So general hardware risks are fairly high in terms of their occurrence. Static discharge is another risk within an organisation, and that also has a fairly high chance of happening. When it comes to errors on systems, input error is one of the highest risks. Programming errors are also fairly high, and operating errors are also a high probability of risk. When it comes to system compromise, then we might have loose documents, an improper release, improper marking, and also ex-employee access. We can see here that the biggest risk is typically with improper marking, and that a document could be marked incorrectly and then go to the wrong person. For password compromise, we have system entry as a risk, and uncleared visit, which could in some circumstances give quite a high risk factor. For fire, then obviously the risk of an explosion is a fairly low probability, along with a catastrophe. A minor fire has a higher risk. For forced entry, we might have burglary. That typically relates to the area and country and environment of the organisation. Vandalism is fairly high risk, along with a disgruntled employee. Terrorism actually has quite a low risk probability associated with it. With lightning, it obviously depends on the place where the organisation is based, and it can go up to fairly high risk factor. And power failure is also another fairly high risk. External power is fairly low compared to an irregularity inside the organisation or an insufficient power supply. So the organisation might look at the risks involved on the organisation, and then they might come up with an annual loss expectancy value. And with this, we look at the cost, we look at the likelihood of an event, and then from the cost we can multiply with the likelihood and get the ATE. So in this case, the risk of a major fire has been assessed as £16,200. Lightning strike is seen as a 0.3 chance of happening, and we can see here all the elements that would be required if a lightning strike hit a network. So in this case, 2,700 is seen as the annual loss. A long-term power loss, the likelihood is 0.1, and again we take the cost in this lost time, data recovery, bad press, loss of business, and so on. We can see here that we have a £16,000 annual loss. So it's with these values that we decide the actual cost per year. And with this cost, we can decide whether we mitigate against something or not. So in this case, a £16,000 hit per year might be enough to justify a UPS system on an internal power generator. The biggest problem with risk is that it's typically different contexts for it. And overall, there is a business context, and that typically focuses on the income or loss of income to a company, or the loss of face. And there's a technical context, which typically involves loss of data, loss of systems, loss of power, and so on. And the major problem that we have is to try and get the business people to be able to communicate with technical people in some coherent way in terms of risk. One way is to define an ontology. So in this case, we have a threat to the organisation. which may reduce an asset value of a certain asset inside the target of our evaluation in a certain context. And again, a threat may exploit a vulnerability which opens up a risk which contains a certain likelihood of an unwanted incident and has a certain consequence. So we can see here that an ontology allows us to define the key terms that we might want to use so that it has a business context and also a technical context. When it comes to the management of risk, then we can also define a basic framework for this. We can establish a context for the risk, identify it, then try and analyse the risks involved, especially for the frequency, consequence, and also for the level of risk. Then we can actually evaluate these risks, and then we do our cost benefit and decide whether we accept a risk or not. If we do not accept the risk, then we need to treat it in some way. Otherwise, we monitor and review. At each of these stages, we want to be able to consult and communicate with our staff to make sure that everyone in the organisation understands the risks involved. And along, we make sure that we monitor and review our processes. A key element of security is the security policy. And with this, we typically take the aims and objectives of an organisation. We take its legal, moral and social responsibilities. And a key element is that we also take the technical feasibility and we feed these in to defining our overall policy for the organisation. It is then up to typically the IT personnel to then implement that policy, and that could be in terms of operating system rights, domain rights, firewall rules, event logs, application rights, and so on. Then, once it is in place, it is important to evaluate how well it actually matches the policy definition, and it may be possible to update and refine this policy. This continual refinement is important in any organisation to make sure the continual focus of the security policy. Along with this, we need to make sure that it's actually working correctly. So in our policy implementation, we typically add in some auditing facilities to make sure that it's working. And then this is then verified, and again, this can be used to inform the policy. External auditors and also internal audits can actually look at these audit logs to make sure that everything is working as it should. So the key elements of a policy, the policy that we have, is to obviously protect our system, to deter, to log, react to a security event, recover, and also to audit and verify. So there'll be more information on these areas near the end of this lecture. So an example of a security policy in implementation is for web applications. Have a web.config file, and this is an XML definition of what's allowed to actually happen on that file. Okay, so let's look at the threats that a system or organisation might face. One of the most difficult to mitigate against is visual spying, and that can involve an intruder actually watching the keystrokes or mouse clicks of a user in order to determine their password, user ID and other details. It is fairly difficult to mitigate against this apart from improving employee training to make sure that they keep their keystrokes secure, especially when they're signing into things. Misrepresentation is another difficult one, in that someone can send an email or phone up a user and ask them for the username and password by saying that they are IT support. And many users will actually give back their user ID and passwords. Eavesdropping is another particular problem, and the eavesdropping involves listening to the communications between users and systems. And the important thing here is that if communications are to be kept secure and secret, then encryption should be used for this communication. Another particular problem, and one that is growing, is logical scavenging, and that involves looking over discarded hard disks, USB drives and disks for data. And the key thing with this is that even though it looks as if files have actually been deleted, there can still also be a remnants of parts or complete files available to someone who is scavenging the data. It is important that data systems are always set up so that there is a complete erasure of all the data on the disk before it is discarded. Interference is a particular problem, especially in wireless networks. If there is a corporate wireless network, then an intruder could set up a high-powered radio transmitter outside the network, and this can actually jam the whole of the corporate network. It may also be possible to set up a transmitter at the same frequency, same channels, so that there is a reduction in the quality of the service on the wireless network. There's also physical attacks and physical removal, which are difficult to mitigate against. Equipment should be locked up in secure areas, network equipment especially. A particular growing problem is spoofing, where a device can be spoofed. For example, in a wireless access point, if someone normally connects to a corporate wireless access point, an intruder could come along and set up their own access point with the same name and same details as their main access point. The user could then connect to this, and the intruder could actually take their data. Impersonation is also a particular problem, and that's where a user pretends to be someone else that they aren't. We'll see an example of this in a little minute. Piggyback is typically where we take valid information and then an intruder can piggyback information or programs on the back of this. An example of this is with an email containing a virus, where the virus has piggybacked itself into the email. Network weaving involves the intruder setting up a network weave where it's fairly difficult to actually find out the original source of the intrusion, and that's typically involving confusing the routing process. Trojan Horses are programs which are made to look valid but will typically do damage. So in this case, a Trojan horse could be a program, an illicit program inside an email when the email is opened, the program will run. It might also be an enticing link. You can see here, best project ever, click. And once the user clicks on it, then it could install a Trojan horse on the machine. These Trojan horses can be fairly quiet in their operation and stay dormant for some time. Then they could become logic bombs, which are typically triggered by an event or at some time in the future. Worms and viruses have been a particular problem. Viruses can also typically self-replicate themselves. And a worm itself, the focus of a worm is typically to use up either a network resource or a host resource, such as CPU usage, disk or network, or even the memory. And a worm will typically spread by replicating itself. 1 becomes 2, 2 becomes 4, and so on. Many security systems now detect the spread of worms, so we can get what are called slow burning worms, which are slow to replicate themselves, but can still spread over a network. Another particular problem is denial of service, or DOS. In this case, we have the intruders, which are Eve, which might be small programs running on each of the hosts, and they have been set up to access a certain resource, in this case the web server, over the network. So it might be that this web server becomes exhausted in coping with the requests from Eve, so that Bob cannot get the required quality service when he tries to access the web server. We can also get network exhaustion, where there is so much traffic at certain parts of the network that Bob again cannot get his requests through. So there's two types of denial of service. One is core denial of service, where it's one machine or one host which does the requesting of the services. In this case, it's fairly easy to protect against this, in that we find out the nearest firewall and block all accesses. A distributed denial of service, or DDoS, is where there are many hundreds, thousands, or even millions of distributed agents across a wide network, and it's almost impossible to block access, as blocking it from one domain could block the rest of the domain. Inference is another problem that we can have, and that's where an intruder could exploit a database weakness using inferences. So if we take an example, in that it is possible to get the average mark for our students, but it's not possible to get individual marks. An intruder could then exploit this. If they do 3 accesses, the first case they take the average of Bob and Alice, the second case the average between Bob and Eve, and then the third case between Alice and Eve. Once you get the averages, if we take average 1 minus average 2, then we get Alice minus Eve upon 2, and then we add on the third average, then we end up with Alice's mark. So Alice's mark is the first average minus the second plus the third. So we take an example of this. Bob got 10%, Alice got 20, and Eve got 30. So the average of the first one is 15. The average between Bob and Eve is 20, and the average between Alice and Eve is 25. If we plug these in, 15 minus 20 plus 25, we see that Alice's mark is 20. So the intruder has managed to infer information from a query which was not valid. It is important to understand inference, in that key information might be given out just by inferring information from certain queries. Another problem might be covert channels, and covert channels involve sending extra information inside a valid channel. We can see here 2 data packets have been sent between Bob and Alice, and Bob has, or Eve has managed to add on a character G with inside the network packet TTL, and then an O, so that on the other side, whoever reads the covert channel could actually read this message, even though the main message is a valid one. The two main types of covert channels are what are called storage channel. That's where we modify an object. In this case, the object is data packets. Or it is possible to do it through a timing channel. So for example, if Bob accesses a certain website at a certain time, that's taken as a binary 1. If he doesn't, it's a binary 0. So later in these series lectures, we'll have a look at covert channels. Then we might also have an active attack, and an active attack will typically exploit some weakness in the system. So in this case, it might be that this causes a buffer overflow when there is a long string in the access. So we can see here, if the system is not protected, somebody could try and log in with an extremely long username, and that could cause the system to act incorrectly. There's authorization attacks, and this involves trying to gain access to a higher level from a lower level form of entry. Trapdoor impersonation is a particular problem where a user is faced with what looks like a valid entry to a system. In this case we have eBay, but unfortunately it isn't the real eBay. It is one that is impersonating it. As far as the user knows, then this is a perfectly correct website. It has all the correct graphics, but we can see here that the domain is incorrect. So an example of this might be this email, this real email. And we can see here when we run the whole of this area is a graphic which is always a particular sign that it could be a trapdoor. And when we run our cursor over it, we can actually see that the link actually doesn't go to where it says it does, even though it says this is the link in the text. It is this link here where we can see a certain IP address on a certain port, 680 is the destination. So we've got this is a spoofed email address. Any email address can be put in here. The URL looks very suspicious, and then when we do a lookup, we actually find that it ends up not in eBay, but some destination Korean website. When we actually look at the actual contents of the email, we can see here that the actual sending of the email was not verified through some server. If it had come from eBay, then there would have been some verification of the original sending email server. An example of phishing is this, and this is an example of putting pressure on a user. So you can see here that many people are worried about their eBay ratings, and they don't want bad feedback. So in this case, you can see here it's almost a pidgin English question, which is quite worrying for the user. Unfortunately, once the user clicks this button here, they will be asked to put their username and password in, and that will go to the intruder. Again, all the links look correct, but when we run our cursor over them, we can see there that the destination IP address isn't the same one as what is in the email message. We can also get ones related to a security problem. Many users are worried that their password could have been changed and so on. And again, this link doesn't actually go to where it says in the link. Okay, so here's another example of that. And again, it looks as if there's been some contact here for the user. When we look at this one actually gives the user ID and login within inside the email, but we can actually see when we look at the actual code within inside the email, then the action on the button here is to send it to a check email site, which is fairly generic for receiving email messages. It is likely once it's received there, it will then get sent to the intruder, and the user's user ID and password could be compromised. There are various key principles involved in security, and this section looks at some of the most important ones. One that we have is defense in depth, and that has a military analogy where we typically use low-level defense for a first-line defense, but more tougher, second line, third line tougher still, and then fourth line high defense. For this, we typically use different layers of defense and make sure that if an intruder breaches one level of defense, then it can take some time to breach the next and the next. And we can also have what are called intrusion detection agents at each of the levels to be able to detect that there's been an attack or a breach of a line of defense. So defense in depth tries to put as many boundaries in the way of an intruder as possible. The first level could be a fairly generic defense, could be a firewall. Then we go up maybe with a username and password, then up through the privileges, could be some biometrics login for a user, and then at the end it could be some physical token. We also have the principle of a demilitarized zone, where we have our side, which is trusted, we have outside, which is untrusted, and then we have a place where the trusted and untrusted can meet, and that's defined as the demilitarized zone. It is in this zone that we can enhance security or relax it. So a system that we might have is that we might have a defense such as a firewall here, demilitarized zone. We might isolate our network from outside and set up intrusion detection systems and so on. Defense in depth is all about setting up many obstacles for an intruder to get over before they can actually compromise a system. Because security is a fairly complex entity to analyze, we typically break it up into various levels. So the OSI model allows us to break the data communications over a network into various layers. So we take the data itself, we pass it into some application protocol. This might include HTTP, FTP, and so on. Then we use some sort of secure connections, such as for we use a connection transport, such as TCP. And the network identifies the network source and destination, such as for IP level. Then we have the data link and physical layers, which typically identify the network that we're using. So the protocols that we typically see here are IP. The protocols here are TCP, and we might get HTTP if we're using a web page. The biggest problem is that these protocols are seen as being fairly insecure. So HTTP and so on are now being replaced by HTTPS, SSH, SFTP, and so on. For TCP, we can see that we get secure sockets and proxy servers. At the IP level, we have network address translation and firewalls. At the data link level, we can have web encryption keys for wireless and so on. And then at the physical level, we can have the actual physical protection of the equipment using padlocks, fiber cables, and so on. If we want to keep our core data secure, then we might use encryption initially. There is another model, which is the internet model, which is equivalent, and it typically merges these three top layers into one, and also merges the data link layer into the network layer. So overall, we've looked at some of the key fundamental areas, including risk and especially a cost-benefit analysis. We looked at the basics of a security policy, and then looking at some of the threats, phishing, denial of service, and so on. And then finally, we looked at some of the key principles involved, such as the demilitarized zone and also defense in depth.